All right, in this video I want to talk about determinants of a matrix. This is going to officially start chapter 3 for us. And the idea in chapter 3, so chapter 3 is all about determinants and what the determinant's going to tell us. So let me just remind you of a few things that we already know, and then we'll build on that as we go. So if we have a matrix, say M or A, let's use A, and this matrix is the matrix A, B, C, D, we have already talked about, or at least we've already seen a context where we've discussed what's called the determinant of A, and the determinant of a 2 by 2 matrix is just going to be AD minus BC. So what you do is you take these two terms and multiply them, the ones on the diagonal, and then you subtract the product of the other two terms. So it's AD minus BC. And that's the determinant of A. And we've already seen, we already know that A inverse exists. This matrix A has an inverse if and only if the determinant of A is not 0. So in other words, if A has an inverse, the determinant's not 0. If the determinant's not 0, then it has an inverse, and all the other combinations. So if the determinant is 0, then there's no inverse, and if A has no inverse, the determinant is 0. So those are equivalent statements. So we've already seen that the determinant of A is going to be useful. What I want to do is I want to actually take one step up and talk about determinants of 3 by 3 matrices. And to do this, we need to do a few things. So there will be a few steps in this process, but first I just want to describe how to find the determinant of a 3 by 3 matrix, and then we'll have some nuances. So now let's consider the matrix A, which is going to be A, B, C, D, E, F, G, H, I. Okay, where those all just stand for generic real numbers. I know I'm using E and I, but they're just meant to be variables of real numbers. So that's going to be a generic 3 by 3 matrix. And what I want to do is let's define the determinant. And there's a few different ways that you can do this. You can actually expand along any row or any column. Okay, so you can expand along any row or any column. I'm just going to start by expanding along the first row, first column. And then I'll explain later how to do this over any row and any column. So the way that this is going to work is that I'm going to look at the first row. So I'm going to expand along the first row. And so we have A, B, C. And what I'm going to do is I'm going to take the A term, and then since I'm looking at the term in the first row, first column, I'm going to scratch out the other values in that row and column. I said that backwards, but in that row and column. So I'm going to scratch out those terms. And then we're going to get the term A times the determinant of what's called the 2 by 2 submatrix. So again, that's the 2 by 2 matrix that we get by deleting the first row, first column of A. So the determinant of A is going to be little a times the determinant of the 2 by 2 matrix E, F, H, I. We're going to alternate terms in the determinant. So next, we're going to have minus B, and then we'll do the same. We'll cross off that row and that column. We get a 2 by 2, what's called a submatrix. That is just the 2 by 2 matrix you get if you deleted the first row and second column. And so we'll multiply by that determinant. So this is B times the determinant of D, F, G, I, plus C times the determinant of the 2 by 2 matrix that you get if you delete the first row and third column. So that's D, E, G, H. D, E, G, H. And then determinants of 2 by 2 matrices we've seen. So this is A times EI minus FH minus B times DI minus GF plus C times DH minus EG. Of course, this formula is never to be memorized. The process is to be memorized. Okay, I don't care about the formula, I care about the process. And that's how we find the determinant of a matrix using the first row. Now you can actually do this with any row in any column. There's a few tricks. Actually, for 3 by 3, there's a trick that I should just mention here. If you take your matrix, so we have A, B, C, D, E, F, G, H, I, and then I'm going to copy down the first 2 columns again. Okay, you can actually compute the determinant by thinking about products along a diagonal. So you would get A, E, I plus B, F, G plus C, D, H. So you add these terms, and then you subtract the terms that you get by looking at the other diagonal. So G, E, C, H, F, A, I, D, B, and then you subtract these terms. So that's a trick that can work for 3 by 3. That's a trick that'll work for the determinant of a 3 by 3 matrix. Okay. In general, if you have a higher order matrix, if you have a 4 by 4, you can do basically the same trick. So let's call these, I don't want to use A, B, C, and D anymore, but let's call these A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, and A34, and then A41, A42, A43, A44. Okay, so if I wanted to compute the determinant of this ridiculous matrix, we would do the same process again if we expanded along the first row. The determinant of A, what you would do is you would look at the value in, if we're expanding along the first row, so if we're expanding along the first row, we would look at the value A11, and then the determinant would be A11 times the determinant of the 3 by 3 submatrix that we would get. So that would be the matrix that we get by deleting this first row, first column. So A22, A23, A24, and so on. So you get the determinant of A2. I'm going to cheat slightly here. I think I copied too much. Yep. So you get this determinant of the 3 by 3 matrix. And then minus A12 times the determinant of the corresponding submatrix that you get by deleting this row and this column. So you get minus A12 times the determinant of that 3 by 3 matrix, okay, and so on. We'll do some examples. We'll do some concrete examples as we go along, okay? That's how we expand along the first row. And of course, if you have a 5 by 5 monstrosity, and I would never do this to you, but if you have a 5 by 5 matrix, you would do the same thing. Okay, so you just do a using one row, just go across. I think it's important at this point, though, to talk about how to do this, not along the first row, but along any generic row. And so let's go back to looking at a generic 3 by 3 matrix. Let's do A11, A12, A13, A21, A22, A23, and A31, A32, A33. All right. And what I want to do is I'm going to think about the sign of each of the values in here. And what I mean by that is that I'm going to kind of superimpose on this matrix. This has nothing to do with what the actual numbers are, whether the actual numbers in the matrix are positive or negative. It has to do with its place in the matrix. And so I'm going to think about the sign here as starting with a plus in the top left and then alternating along each row and column. So minus, plus, minus, plus, plus, minus, minus, plus. Okay, so I'm going to kind of associate each position with a positive or negative number. Again, not worrying about the actual number that is A12 or A22 or A32. So I don't care about what the actual value is. I'm just thinking about this position that each value in the matrix is as being positive or negative. And so if we were to expand along, let's do it this way with a concrete example here. Let's look at the matrix A being 1, 2, 3, 4, 5, 6, 7, 8, 9. And so we can expand along the first row like we did before. So I think this is worth just writing again. So as a calculation, we'll do the determinant of A is 1 times the determinant of the 2 by 2 matrix, 5, 6, 8, 9. So that's going to be 5 times 9 minus 6 times 8, minus 2 times the determinant of the corresponding 2 by 2 submatrix, so 4, 6, 7, 9. So it's going to be 4 times 9 minus 6 times 7, plus 3 times the determinant of the 2 by 2 submatrix, 4, 5, 7, 8. So that's going to be 4 times 8 minus 7 times 5. And that's going to work out to be 45 minus 48. So it's minus 3. Minus 2 times, let's see, 36 minus 42. So we'll get to that in a second. Plus 3 times 32 minus 35. So altogether, this is going to be negative 3. 36 minus 42 is negative 6 times negative 2 is going to be plus what? It's going to be plus 12. And then the final step will be plus 3 times minus 3, so minus 9. And this one happens to work out to be 0. So the determinant of A is 0. What's true about determinants is that actually it's not just 2 by 2 matrices, but since the determinant of A was 0, it turns out that A does not have an inverse. And we'll talk about that in a second. Does not have an inverse. Okay, so since the determinant was 0, A does not have an inverse. Let's do the same calculation though, but using a different row or different column. Let's say the second column. So I'm going to copy our matrix here. And there's nothing special about the first row. So there's nothing special about it. Let's expand along the second column. So what we're going to do is I'm going to pick out each value in the column and then multiply that by the corresponding determinant of the 2 by 2 submatrix that we get by deleting all the values on the row and column that we're choosing. So this is going to be 2 times the determinant of 4, 6, 7, 9. And then 5 times the determinant of, let's see, if we get rid of all the values in this row and column, we're left with 1, 3, 7, 9. And then 8 times the determinant of the 2 by 2 submatrix that we get by deleting the third row, second column. So 1, 3, 4, 6. And then our final step is that in front of each of these numbers, we have to go back to our sign chart and put the signs of each of these positions. So if we remember our sign chart, we were looking at the second column. So that means that the top value is negative, the middle one is positive, and negative. So this will be negative, positive, negative. And again, if you know the sign of the first term, that just alternates. And so we can compute that this will be negative 2 times 4 times 9 minus 6 times 7 plus 5 times the determinant of 1, 3, 7, 9. So that'll be 1 times 9 minus 3 times 7 minus 8 times the determinant of 1, 3, 4, 6. So that's 1 times 6 minus 4 times 3. And so altogether this will be, we should get 0, but let's just double check. Negative 2 times negative 6 plus 5 times, let's see, 9 minus 12 is negative 12. 9 minus 21 is negative 12. Minus 8 times negative 6. So this is going to be altogether 60 minus 60, which will really be 0. So negative 12, I'm sorry, positive 12 minus 60 plus 48. So yeah, we get 60 minus 60, which is 0. And we should get the same value for the determinant regardless of whether we expand along the first row or second column or third row or whatever row or column we want, we should get the same value.